Hello students, welcome to second lecture of solutions. In first lecture we discussed about four different type of units of concentrations or four different type of measurements of concentration, and let's start with fifth one, which is mole fraction. So mole fraction can be considered as ratio of number of moles of compound versus the number of moles total inside the solution. As for example, as the expression suggests or equation suggests, mole fraction of the compound is equal to number of moles of compound divided by total moles of all the components. That means suppose we have three different compounds, let's say A, B and C. These three are different compounds in a mixture or in solution. So let's say number of moles of A is equal to 2, number of moles of B it is equal to 3, and number of moles of C it is equal to 5. So total number of moles, that means A plus B plus C, is equal to 10. So total number of moles are 10. So mole fraction of A, which is represented as XA, is equal to number of moles of A, which is 2, divided by total number of moles, it is equal to 10. So XA is equal to 0.2. Similarly for B it will be 3 divided by 10, for C it will be 5 divided by 10. So mole fraction of B is 0.3 and mole fraction of C is equal to 0.5. And always total mole fraction will be 1. Just like the percentage, total percentage is equal to 100, and similarly total mole fraction or fraction will be 1 always. So if you want to convert the mole fraction into percentage, you have to multiply the mole fraction with 100. That means let's say total number of moles is equal to 10 and total is equal to 100%. So total number of moles in percent is equal to 100 and total number of moles in fraction is equal to 1. Similarly, mole fraction of A is 0.2. If you multiply 0.2 with 100, you will get 20. So total we have 10 moles, and out of 10 we have 2 moles of A. So it is 20% of A. So in fraction it is 0.2 and in percentage it will be 20. Similarly, B is equal to 30%, C is equal to 50%. In fraction accordingly it is 0.3 and 0.5. So as mentioned, suppose we have two different compounds in a mixture, that means we have binary mixture, and number of moles of A it is equal to Na and number of moles of B it is equal to Nb. So mole fraction of A is equal to number of moles of A divided by total moles. Here we have two different compounds, that's why total number of moles of two compounds. So as a common equation, as for example, suppose we have total I number of components. So mole fraction of a compound is equal to number of moles of that compound divided by total number of moles. That means number of moles of I divided by summation of all the elements, number of moles of all the elements. And as already said, total number of mole fraction is equal to 1 always, no matter how many different elements you have, 1, 2 or 1000, doesn't matter. Total mole fraction will be always 1. Mole fraction unit is very useful in relating some physical properties of solution, say as vapor pressure with the concentration of the solution, and quite useful in describing the calculations involving gaseous mixture. Now let's discuss this numerical. Calculate the mole fraction of ethylene glycol C2H6O2 in a solution containing 20% of C2H6O2 by mass. So first, for mole fraction we need number of moles of each component present in mixture, and to find number of moles we need mass and molar mass. So here we have ethylene glycol, and as mentioned it is 20% solution by mass. So that means if we have total 100 grams of solution, out of 100 gram 20%, which is 20 grams, represents mass of ethylene glycol, and remaining 80% will be our solvent, which is water in this case. If nothing is mentioned, then water will be the solvent. If a specific solvent is mentioned, then we have to calculate according to that solvent, but here nothing is mentioned, so we considered 20 gram is the mass of ethylene glycol and 80 gram is the mass of water, and total mass of the solution will be 100 grams. We used 100 because it is easy to calculate. 100 gram it is equal to 100%, then the percentage of the given compound directly represents mass of that compound. That's why we used 100 gram. You can use any other value, but it will slightly increase the complications in calculation, and that's why we are choosing the simplest figure, which is easiest to calculate. So now we decided the masses of each compounds, and now let's find the number of moles. So molar mass of ethylene glycol is equal to 62 grams. You can calculate it yourself. We have 2 carbons, so 24 total 6 hydrogen, that means 6 grams from the hydrogen, and 2 oxygens, that means 32 from the oxygen. Total is equal to 62 grams. And we know the mass of water, molar mass, which is 18. So how can we find the number of moles? So number of moles is equal to mass divided by molar mass. So mass of ethylene glycol is 20 grams because it is 20% solution, and molar mass is 62. So number of moles of ethylene glycol is equal to 0.332. And we have 80 grams of water, so 80 divided by 18, which is molar mass, and is equal to 4.444. So next, the mole fraction of ethylene glycol, it is equal to moles of ethylene glycol divided by total moles. So number of moles of ethylene glycol, it is 0.332, and total is equal to 0.332 plus 4.444, and it is equal to 0.068. It is the mole fraction of ethylene glycol. Now as mentioned earlier, number of moles of water can be found with the similar method. Number of moles of water, it is already available, and mole fraction is moles of water divided by total moles, which is equal to 0.932. And you can find it without doing this calculation, and we need the value of mole fraction of other compound. Subtract the value of mole fraction of the compound from 1, and you will get mole fraction of other compound. As mentioned here, 1 minus mole fraction of ethylene glycol is equal to mole fraction of water, because total mole fraction is always 1. Next is molarity. Now this is one of the most important concentration measurement method, and in practical we need this to calculate and to prepare certain solutions. As for example, first practical of 12th is volumetric titration of KMnO4 versus oxalic acid, and KMnO4 solution is unknown, and you have to find the concentration of KMnO4, and oxalic acid is 0.1 molar in that practical. That means we need 0.1 molar oxalic acid, and you have to prepare it yourself. So for that we need this calculation. So molarity is defined as number of moles of solute dissolved in 1 liter or 1 cubic decimeter of solution. That means number of moles of the solute in 1 liter solution is directly represented as molarity of that compound. So molarity is equal to moles of solute divided by volume of solution in liters. That means 0.25 mole per liter or molar solution of NaOH represents we have 0.25 moles of NaOH in total 1 liter solution. And similarly, if you want to prepare any other quantity, then you can follow the same thing, moles of solute and divide by volume of solution in liters, and you can find the concentration in molarity. As here we have an example, calculate the molarity of solution containing 5 grams of NaOH in 450 milli of solution. So first we need to find number of moles of NaOH in 5 gram. Now molar mass of NaOH is 40 grams, so 5 divided by 40 is equal to number of moles, which is equal to 0.125. Now total solution we have 450 milli, so you have to convert it into liters. So 450 divided by 1000, which is equal to 0.45. So we have 0.125 moles in 450 milli, that means 0.45 liters, which is equal to 0.278 molar. So simply this value represents we have 0.278 moles of NaOH in 1 liter of solution. That means per 1 liter, this is the quantity of number of moles of NaOH. Next one is also an important measurement quantity techniques, molality. So molality is defined as the number of moles of solute per kilogram of solvent, as it is expressed as moles of solute divided by mass of solvent in kg. Now keep in mind, main difference between the molality and molarity is, in case of molarity we have number of moles of solute divided by volume. This is the first difference. Here we have mass, and in molarity we have volume of solution. Okay, so these are the two differences. In molality or small m, we have mass of solvent alone, not solution. In case of molarity, we have volume of solution. That means combined volume of solvent and solute. On the other hand, in molality, small m, symbol of molarity is capital M. For molarity, it is small m. So molality represents number of moles of solute in quantities measured in mass and for solvent only. And in molarity, we have number of moles of solute in quantity is measured in volume and volume of solution. For example, as mentioned, 1 mole per kg represents 1 mole per 1 kg of solute. So as mentioned, for KCl we have 1 mole, that means 74.5 grams of KCl, and it will be dissolved in 1 kg of water. So all of these methods have their own importance, and all of them have their own benefits and downgrades. So mass percentage, ppm, mole fraction and molarity are independent of temperature. That means temperature do not affect these values because they are dependent on mainly on mass. And as we know, mass is independent from the temperature. If you increase or decrease temperature, mass do not change. Whereas molarity is a function of temperature because molarity depends on volume, and with temperature volumes do change. We know that when we heat some solid compounds, usually they expand, and similarly when we heat the gas, they also expands. So because of that, volume changes with temperature, and that's why molarity also changes with temperature. This is because volume depends on temperature and mass does not. So second example, calculate the molarity of 2.5 grams of ethanoic acid in 75 grams of benzene. So both of solute and solvents are mentioned in mass, 2.5 grams and 75 grams. So first we need to convert the number of moles of solutes into moles. So mass is mentioned and we have to convert it into moles. So molar mass of acetic acid is 60 grams. So 2.5 divided by 60 is equal to 0.0417 moles. And we have 75 grams of benzene. So we can put cross multiplication. If 75 grams of solvent contains 0.0417 moles, then 1 kg, that means 1000 grams is equal to how many? So 1000 multiplied by 0.0417 divided by 75. Okay, so same thing is mentioned here. 0.0417 multiplied by 1000 divided by 75, which is equal to 0.556 moles per kilogram of solvent. So that means this will be the molality, small m, of ethanoic acid solution in benzene. Here 5 different examples are mentioned. Try to calculate it yourself. If you find any difficulty or if you don't find the answer, then ask me, we will discuss it in next lecture. Our next point is solubility. Solubility of substance is its maximum amount that can be dissolved in specified amount of solvent at specified temperature. So that means temperature has effect on solubility. Depending on the physical state of solute, temperature may increase or decrease the solubility. It depends upon the nature of solute, solvent and on temperature and pressure. Let's consider the effect of those factors in the solution of solid or gas in liquid. So first is solubility of solid in a liquid. Every solid does not dissolve in even a given liquid. While sodium chloride and sugar dissolves readily in water, naphthalene and anthracene do not. On the other hand, naphthalene and anthracene dissolve readily in benzene, but sodium chloride and sugar do not. So it depends on interaction between the solvent and solute molecules. It is observed that the polar solutes dissolve in polar solvents and non-polar solutes in non-polar solvents. In general, the solute dissolves in solvent if the intermolecular interactions are similar in the two, or we may say like dissolves like. So similar molecules usually attracts each other. Polar molecules attracts polar molecule, that's why they have strong interaction, and non-polar attracts non-polar, and that's why they have stronger interaction, and that's why they will mix properly with each other, which is called solution. When a solid solute is added to the solvent, some solute dissolves and its concentration increases in the solution. This process is known as dissolution. Some solute particles in solution collide with the solid solute particles and get separated out of the solution. This process is known as crystallization. That means if solid is dissolved inside the given liquid or solvent, then it is called dissolution, and if it is separated out from the solution, okay, if it is mixed with it, then it is dissolution, and if it is separated out, then it is called crystallization. A stage is reached when two processes occurs at the same rate. Under such condition, number of solute particles going into the solution will be equal to the solute particles separating out, and a state of dynamic equilibrium is reached. So as mentioned, solute plus solvent gives solution, and when solution separate out, it gives solute and solvent, and at equilibrium both of these reactions will be at same rate. At this stage, the concentration of solute in the solution will remain constant under the given condition, that is temperature and pressure. Similar process is followed when gas are dissolved in liquid solvent. That means gaseous particle will enter in solution and it will convert into liquid state, and already dissolved gaseous liquid will come or will evaporate in gaseous state. And when both of this reaction gains equal rate, we can say that equilibrium is attained. And when equilibrium is attained, no addition or no more dissolution will occur. Such a solution in which no more solute can be dissolved at the same temperature and pressure is called saturated solution. Now keep in mind, if you change the temperature, or that means if you increase the temperature of the solid solute in liquid, you can dissolve more amount. That means with increasing temperature, amount of solubility also increases. An unsaturated solution is one in which more solute can be dissolved at the same temperature. The solution which is in dynamic equilibrium with undissolved solute is saturated solution and contains the maximum amount of solute dissolved in given amount of solvent. Thus the concentration of solute in such solution is its solubility. So maximum amount which can be dissolved is called solubility. If you add more amount than the solubility, then excess quantity will remain undissolved and you will see it at the bottom of the vessel. That means, let's say if our solubility of NaCl in water is 100 grams. So you can dissolve 100 grams of NaCl in 1 liter solution, 1 liter of water at max. If you add 110 grams, then 100 gram will dissolve and 10 gram will be present at the bottom of the vessel undissolved, that means in solid form. Earlier we have observed that solubility of one substance into the another depends on the nature of substance. In addition to this variable, two other parameters, that is temperature and pressure, also control this phenomenon. But solids are effectless from the effect of pressure. That means pressure has no effect on the solid solubilities. So effect of temperature, the solubility of solid and liquid is significantly affected by the temperature changes. Consider the equilibrium represented by equation 2.10. Being dynamic equilibrium must follow Le Chatelier's principle. Le Chatelier's principle is already discussed in previous standards, but if you find any difficulty, then feel free to ask. We can discuss it in detail. In general, if in a nearly saturated solution, the dissolution process is endothermic, that means it requires heat. The solubility should increase with a rise in temperature, and if it is exothermic, the solubility should decrease. This trend also observed experimentally. Usually, solubility of solids with temperature increment increases. That means, let's say if we dissolve the sugar in water, solubility of sugar, let's say it is 100 grams. So 1 liter water can dissolve up to 100 grams of sugar at 25 degrees Celsius temperature. But if you increase the temperature, you can dissolve more amount of sugar. At 50 degrees Celsius, let's say you can dissolve 10 grams more. So total solubility at 50 degrees Celsius will be 110. At 100 degrees Celsius, let's say you can dissolve even more 10 grams. So at 100 degrees Celsius, our solubility of sugar is 120 grams. At 25 degree it is 100, at 50 degree it is 110, and at 100 degrees Celsius it is 120 grams. Next is effect of pressure. So pressure does not have any significant effect on solubility of solids in liquid because these compounds are incompressible. It is so because solid and liquids are highly incompressible and partially remains unaffected by change in pressure. Next is solubility of gas in liquids. Many gases dissolve in water, and usually their solubility are very low, that means poor solubility. Oxygen dissolves only a small extent in water. It is this dissolved oxygen which sustain all aquatic life. We know that living animals or organisms requires oxygen, so sea creatures usually uses oxygen which is dissolved in water. On the other hand, hydrogen chloride gas is highly soluble in water. So hydrogen chloride we use inside the laboratory is actually hydrogen chloride gas dissolved in water. It is not pure liquid. It is solution of HCl in water. Solubility of gases in liquid is greatly affected by pressure and temperature. Solubility of gases increase with increase of pressure, because if we increase the pressure, we are actually increasing the concentration of the gases. Understand it like this way. Suppose we have a container, airtight container, and let's say we have total 10 moles of gas in this container, and volume of this container is 1 liter. Okay, so each dot, let's say it represents 1 mole of gas. So total number of moles of gas, it is 10, and 10 mole of gas is present in 1 liter. So we can say that we have 10 moles per liter. Now if we compress this gas by applying pressure, suppose we have a movable piston on the top of this container and we can move it. By applying pressure, let's say we decrease the half of the volume. That means now volume is half of the initial, so we have 0.5 liter of solution, but it doesn't change the number of moles of gas. So now we have same number of moles of gas but in less volume. So we have total 10 moles of gas in 5 liter. That means we have 20 moles per liter now. So as we decrease the volume, obviously pressure is going to increase. According to PV is equal to nRT rule, we are changing the volume. If you are decreasing the volume, then pressure has to increase to become equals to nRT. We are not changing the number of moles, and R is gas constant, so it will be constant, and temperature is also constant during this process. So we can say that number of moles, gas constant, and temperature, all of them are constant during this process. So if you decrease the volume, pressure has to increase. So by decreasing volume, we are actually increasing the pressure, and increment in pressure also increases the concentration. So higher pressure represents more concentration for gases. For solution of gases in the solvent, consider the system as shown in figure 2.1a. The lower part is solution and the upper part is gaseous system at the pressure P and temperature T. So this is our first figure which has comparatively lower pressure. We only applied a single weight on the movable piston. So this portion on upper region represents the gaseous state, and this is our liquid, and all these black dots represents gas dissolved in liquid. That means we have solution at the lower region here. Assume this system to be in state of dynamic equilibrium. That is, under this condition, rate of gaseous particle entering and leaving the solution phase is the same. So here two different reactions are going on. Gaseous molecules are entering in liquid solutions, and liquid solute, already solute particles of gas is escaping from the solution and going in the gaseous state again. And rate of both of these reactions are equal, so no change in number of moles of gas in gaseous state or in solution state changes. Now increase the pressure over the solution phase by compressing the gas into smaller volume as mentioned in second figure. This will increase the number of gaseous particles per unit volume over the solution, and also the rate at which gaseous particles are striking the surface of solution to enter it. So that means by applying pressure on the surface, we are actually increasing the concentration of gas on the surface. If concentration on surface increases, that means more number of gaseous particles will enter inside the solution. Now keep in mind, in figure A, reaction was already at equilibrium, so no change in concentration was observed. But by applying pressure, we are changing the equilibrium, and that's why reaction will move in forward direction. That means gas plus liquid will form solution. So more number of gaseous particles will enter in solution. So that's why the solubility of gas will increase until a new equilibrium is reached, resulting in an increase in the pressure of a gas above the solution, and the solubility increases. So as mentioned in this figure, we added some more weight on the surface. That's why initial volume, and this is the new volume. So obviously volume is shrinked. That's why number of particles in gaseous state are increased per unit volume, and that's why more number of particles will strike on the surface and will enter inside the solution, and we have comparatively higher concentrated solution. Same reaction can be observed when we open the soda bottle. Okay, soda bottle is actually solution of carbon dioxide in water. So when we open the bottle, we can see bubbles of gases coming out of the liquid, and these bubbles are actually already dissolved carbon dioxide. So when we release the pressure from the upper region, dissolved carbon dioxide gas will bubble out. That means it will separate out. So it is opposite reaction of these two. That means inside the bottle we have high pressure applied, so more number of carbon dioxide molecules are dissolved. But when we release the pressure, this additional amount which is dissolved will evaporate. That means it will try to escape from the solution phase. Henry was the first to give a quantitative relation between the pressure and solubility of gas in a solvent which is known as Henry's law. The law states that at a constant temperature, the solubility of gas in liquid is directly proportional to the partial pressure of the gas present above the surface of liquid or solution. Now partial pressure is, suppose we have two different gases, and both of them are contributing in pressure. So gas A and gas B, both of them are providing pressure. So combined pressure is not belongs to only one of the gas. Contribution of first gas is called its partial pressure, and contribution of second gas is called its partial pressure. That means if we have A and B, two different gases, then contribution in total pressure of A is partial pressure of A, and contribution of B is called partial pressure of B. Dalton, a contemporary of Henry, also conclude independently that solubility of gas in liquid solution is a function of partial pressure of the gas. If we use the mole fraction of a gas in the solution as a measure of the solubility, then it can be said that the mole fraction of gas in the solution is proportional to the partial pressure of gas over the solution. Most commonly used form of Henry's law state that the partial pressure of gas in vapor phase is proportional to the mole fraction of gas in solution. And because of they are proportional, if you want to remove the proportionality sign, then we have to place one constant, and in this case our constant is Kh, and Kh is known as Henry's law constant. So pressure of gas is equal to Henry's law constant multiplied by mole fraction of that gas. If we draw a graph between the partial pressure of gas versus mole fraction of the gas in solution, then we should get a plot of type as shown in figure 2.2. And because they are proportional, you will get this type of straight line graph. So we have mole fraction here and partial pressure here. So as we increase the partial pressure on y-axis, mole fraction of gas will also increase, and they are proportional. That's why we are getting a straight line graph. Different gases have different Kh values at the same temperature. This suggests that Kh is a function of the nature of gas. And keep in mind, it also changes with temperature. So different gases have different Kh value, and with different temperature, it also changes. It is obvious from equation 2.11 that higher the value of Kh at a given temperature, lower the solubility of the gas in the liquid. It can be seen from table 2.2, Kh value of both N2 and O2 increases with increase of temperature, indicating that the solubility of gases will decrease. So that means temperature decreases the solubility of gases. On the solid case, if we increase the temperature, solubility of solids usually increases. But for gases, if you increase the temperature, solubility of gases decreases. That means in cold water, more quantity of oxygen can be dissolved at given pressure. But in hot water, dissolved quantity of oxygen will decrease, and that's why this is the reason that aquatic species are more comfortable in cold water rather than in warm water. Now here one example is mentioned. Example number 2.4, nitrogen through the water. So method is mentioned. Let's talk about it quickly. First point, mole fraction of nitrogen, we can find it from the given pressure values. So mole fraction of nitrogen, as mentioned, pressure is mentioned, and as we know, our equation P is equal to Kh into X. So from this equation we can say that X is equal to P upon Kh, and pressure is mentioned divided by Kh value of the gas, which represents the mole fraction. So as we can see, mole fraction of nitrogen is extremely low. Total of mole fraction is always 1, and for nitrogen it is mentioned as 1.29 into 10 raised to minus 5. That means mole fraction of nitrogen is equal to 0.0000129, and total mole fraction is equal to 1. So if we subtract 0.0000129 from 1, you will get the mole fraction of second component, which is water. So subtracting such a small amount from 1 doesn't change the value of 1 much. So we can say that number of moles of water are very higher than the number of moles of nitrogen in the solution. Suppose we have 1 liter of solution. 1 liter usually represents 1 kilogram. So we have 1 kilogram of water, that means total 55.5 moles. If you divide the mass of water, which is 1000 grams, divide by atomic mass, you will get 55.5. So number of moles of water is 55.5, and mole fraction of the nitrogen is very low. So we can say that number of moles of water are very higher than the nitrogen. That means we can ignore the number of moles of nitrogen in calculation. So that's why our equation mole fraction of nitrogen is equal to number of moles of nitrogen divided by total moles. Now total mole is equal to number of moles of nitrogen plus number of moles of water. Now as we discussed already, number of moles of nitrogens are very less than number of moles of water. So we can say that it is equal to 55.5. It doesn't make much difference. And it is equal to 1.29 into 10 raised to 5. We already calculated it. From this calculation, we can find the number of moles of nitrogen, which is equal to 7.16 into 10 raised to minus 4. Now we need it in millimoles. Our question is as mentioned in the question. So what are the millimoles of nitrogen in 1 liter of water? So for converting moles into millimoles, we have to multiply it with 1000. So number of nitrogen in term of millimoles is 0.716 moles.